Welcome, everybody. I'm John Furter, Technical Project Manager for Quest and SMPTE Fellow. And I'd like to welcome you to this session on timing, trust, and transformation in live media workflows. I think we've got two really excellent papers to finish off the day. If you have questions, please use the QR codes. I get to scan them. I get to see them. I will read them out at the end of the presentations. Our first speaker is Allan Armstrong of Mindberg, who will be speaking on protecting broadcast infrastructure from GPS jamming and spoofing attacks. Allan is CEO of Mindberg USA, which is the U.S. subsidiary of Mindberg Funktion GmbH and Company. He has a history of roles in applications engineering, marketing, and business management, and he earned his Bachelor of Science degree in electrical engineering from the Massachusetts Institute of Technology. Allan.
Can you all hear me? Okay, yeah, it's working. Hi, I'm Allan from Mindberg. I'm going to talk about GPS jamming and spoofing and how to protect broadcast infrastructure. This paper is the work of many people in our company and some people in the ecosystem as well. I've got 8 co-authors. I want to mention 2 of my co-authors, Lee Whitcomb, who you all know, and Doug Arnold, who's the chair of the 1588 committee. Doug took a look at the jamming and spoofing situation. There were a lot of papers in the past that were talking about the sky falling. Doug said, no, we have the tools to solve this problem. Let's just go about it sensibly. So I want to talk first about jamming, and then I'll talk about spoofing, but because the two have different mechanisms and there's different tools that we use to solve the problems. I'll then also talk about testing, both lab testing and open sky testing, and I'll summarize by talking about mitigation techniques. Okay, so GPS jamming. Jamming just means a strong radio signal that attempts to overpower the input of a receiver so you can't receive the signal. And yes, there are problems with GPS jamming. Fortunately, most of these problems are professional drivers who don't want to be tracked by their employer. They get a cigarette lighter chirp jammer, and this will jam GPS in a radius of maybe 1 kilometer or less. It prevents their truck or car from recording where they've been, but if they park it at your facility or drive by your facility, it can cause problems. So that's most of the problems. I'd like to talk about some basic protection against jamming. There's 2 main technologies that are the first line of defense. The first one is filters. The GNSS receiver chipset can have some filters. One would be an RF filter. Typically, it's surface acoustic wave technology. It's a bandpass. It knocks out any strong signals that are outside of the GPS band. That's the first line of defense. The second line of defense is some of these receivers also have digital IF filters after the A to D converter, and they can be tuned to identify strong in-band interferers and knock them out. The next line of defense is a holdover oscillator. Typically, these are oven-controlled crystal oscillators. When GPS fell out or is not available, they hold over and they keep timing going reasonably accurately. And the combination of these 2 technologies is sufficient for most civilian jamming issues. Here's a table. We have an even better eye chart with much more data. It shows the amount of drift that you would get for different grades of oscillator for different times. That's basically how you select the oscillator that you might need. Another thing that's important is the use of redundant receivers and redundant antennas, remote antennas. So typically you have a redundant network, red and blue networks, and you have one time server for each. Each time server has a receiver. Each receiver has its own antenna. And you want to place those antennas as far away from each other as possible. The normal design is to put them on opposite corners of a roof. So if someone's jamming one, they probably aren't jamming the other one. In fact, the other one is probably sheltered by the building and the roof. So that's a typical design. It's just important to place them as far away as possible. If you have a lot of space, we can use fiber optic converters to get more distance. It's also possible to have multiple antennas or 2 receivers for each time server. This has a number of small advantages in some cases to give some additional protection. So a really important question is, how serious is GNSS jamming? Well, some years ago, the European GNSS agency put together a project to monitor interference events, and they set up stations in 23 countries. They collected almost 500,000 events, and they got a really long report, actually many really long reports. But the basic conclusion of that report is the vast majority of events are short duration, and that's really good. What that means is that the holdover oscillator does a pretty good job. Since then, there's more information available about GNSS jamming events. There are a number of websites. This one is gpsjam.org. It's the best known one, and it reports GPS jamming events. The way that it does that is that it looks at air traffic control, navigation data, and compares that. The INS data compares it to GPS, and if the two differ, then it assumes that GPS has been jammed. And the interesting thing is that it finds out that the jamming events are mostly in conflict areas, which mostly means around Russia. So this is useful. You can check this every day of the year. You can go back and look at history. This is from January 20th of this year. It doesn't give you a long-term view because it just looks at one data point at a time. But the U.S. Department of Transportation and the DoD have collected some of this data, and they've amalgamated it with some more data to show where GPS jamming is occurring in the world. It's mostly conflict areas, but it's also around military bases. Military bases, they don't want drones flying over them, so they jam GPS. The basic conclusion is if your main problem is these cigarette lighter jammers, life is good. But that's not the whole problem. So you may never see it, but these do exist. This is a photo courtesy of the Russian Defense Ministry. It's nice of them to give us a photo. It's unfortunate that they haven't given us a data sheet for this. But we can infer some things. First of all, there's 3 trucks here. So there's probably a lot of power available, which means they can have high power amplifiers, which mean they can have long range. They also have quite a collection of antennas, including directional antennas and antennas at various frequencies. So these things are really in operation. One of them was destroyed near Zaporizhzhia power plant. I wouldn't want to be working in one of these because when you're emitting that much radio power, it's very easy for a missile to track you. But these systems do exist. There are a number of countermeasures used. These come from the defense industry. The first one is a so-called SIRPA, or Controlled Radiation Pattern Antenna. It uses a phased array of antennas, and it can measure the angle of incidence of a jammer. And then it can tune the receiver array, tune the tap weights, so you don't receive the signal from that jammer. This is used extensively for military navigation applications. It has not been used for critical infrastructure because it has been under export control. The export control was very recently lifted, but there's another type of a much less expensive type of antenna which has been used by a number of customers for critical infrastructure. It's a so-called horizon nulling antenna. It relies on the basic premise that the satellites are up there and the jammers are over here. So if we increase the gain to the zenith and decrease the gain to the horizon, we'll have some advantage. And this, from scientific principles, appears to work. It's been deployed by a small number of customers and some fairly large and some pretty small organizations, and we've not heard any bad information about this. So these are both 2 ways of addressing the problem. Then The real solution, if you are facing military jamming, is terrestrial time transport. And you can get time from various locations like the national standards organizations, like national labs like NIST in the US, or from data centers like Amazon or Hoptroff or Equinix. But you need to transport it over some physical media, and it tends to be a little bit expensive and a little bit complicated. But this is the solution for a real problem. Okay. So, oh, I'm sorry, I was explaining the wrong slide. I just explained this slide. Okay, I apologize for that. Okay, so I've now covered jamming. Let me move on to GPS spoofing. Spoofing is different than jamming. Jamming just means to overpower a receiver. Spoofing, the intent is to trick you into believing something that's not true, like to move the timing in such a way as to disrupt your operations. It's much more common to move navigation. Maybe you want to make a ship hit dock or something like that. So this sounds pretty hard to do, but the truth is, it's not so hard to do it. There are commercially available software-defined radios for really low prices, like $300, and they've got a schematic, and from that schematic you can go look at the data sheets of all these chips. And it turns out I used to work on the same floor as the people who design the RF chips in there, so I can read these data sheets, and they can make 256 and 1024 QAM signals with really good error factor magnitude, and the GPS signals are very well documented, so they can do a good job of spoofing GPS. And worse yet, there's open source software on GitHub to do this. So you can get started. So this could be a serious problem. So the way to deal with this, the first thing to do is to raise the bar on spoofers. So when they go to spoof you, they need to replace every radio signal you're listening to. And typically you've got 8 to 10 satellites in view. So they have to spoof 8 to 10 signals. Well, you can get a multi-constellation receiver which listens to GPS, Galileo, GLONASS, and Baidu. Now they have to simulate 32 or 40 such signals. And then you can get a multiband receiver. All of these satellites broadcast on 3 frequencies. So if you get a receiver that listens to all those frequencies and compares the data, now they have to spoof about 100 or so different radio signals. And when they spoof those, they have to time synchronize the spoofing, so you can't catch them with inconsistencies. So the first thing you should do is have a multi-constellation, multi-band receiver. Okay, now I want to talk about how we ensure that the satellite inputs we're receiving are correct. There's 2 methods for doing this. One we call consistency checks, or anomaly recognition. It's often called RAIM, Receiver Autonomous Integrity Monitoring, which sounds really impressive, and you can brand that. There's many companies that have versions of RAIM or TRAIM or whatever. I call it a consistency check. That's the first thing we do. The second thing you can do is cryptographic authentication to verify that the signal really came from that satellite. So I'd like to talk first about the consistency checks. There's a lot of consistency checks that you can do. The first thing that you would think to look at is to look at the modulation, look at the IQ modulation, and see if it's got a good error vector magnitude. This sounds really impressive, but GNSS signals are very well documented, and the receivers are very capable, so you're not likely to catch much here. The next thing is you can look at how many satellites you're receiving. Well, when they start spoofing, there will be more satellites, and they'll replace some satellites, but the number of satellites is constantly changing as satellites move through the sky, particularly if you're in an urban canyon. So if you do this, there's risk that you get false positives, that you get a false alarm. The next one, you can look at the position. So it turns out most spoofing is intended to crash container ships against bridges, not to mess up time applications. And we know in a time application your antenna is fixed. Therefore, if the receiver tells you that the antenna is moving, they're probably trying to mess with navigation. You can knock those attacks away right away. So this is a pretty effective one. Next, you can look at the power that you receive. The power that you receive from GPS is very close to constant. And they need to overpower GPS, so they need to transmit a higher power than that. If they transmit too high of a power, you can flag that and say, that's not realistic. That must be spoofing. And in addition, they cannot observe your receiver, so they don't know how much power to put out to trick your receiver. So this is a pretty good method. The last method is time. That is that time, in 1 second, time moves by 1 second. And if you have a good holdover oscillator, you can compare the incoming reference against that. So there's a really interesting conclusion here. The complex methods don't work very well. The simple methods work great. And that's kind of surprising. Okay, so let's talk about authentication. That's the next line of defense, cryptographic authentication. There are two services available today. One of them is called OSNMA, Open Services Navigation Message Authentication, and it's part of Galileo. It's free. It just turned on. But it only covers one of the 4 constellations. There's also NMA. It's Fugro Atomicron NMA. I should have put that on the slide. It covers all of the constellations. It's up and running, works well. It is a paid service. So this slide just shows how the Galileo OSNMA works. The important thing here, well, it sends down a cryptographic hash, but this became live as a full operating capability in July of this year. Receivers are available, so this is a pretty strong method. The Fugro Atomicron has been running for a couple years now. It has about 100 ground stations that measure the satellite signals and authenticate those. It beams hash codes up through the Inmarsat constellation, and a receiver can check those against the received signal. Okay, now I want to talk about how they spoof you. There's 4 basic types of spoofing attacks. The first one is what we call a non-coherent or blunt attack. They just stick up another transmitter. And it's pretty easy to catch these with the consistency checks. This one's not hard to defeat. The next one we call break the lock. To start spoofing, they first jam, and they put you into a defensive mode where they're jamming your receiver. And then they take away the jamming at the same time. They pop up the spoofing signal and hope that you lock onto that. So that's a little bit more sophisticated and fairly effective. A lot of receivers fail at that. The next one is called meaconing. They receive a GPS signal. They delay it, maybe with a cable, or maybe with a deep memory buffer. It's much cheaper to do it with a cable. And then they retransmit it. And this is very effective for messing with navigation, but it's quite easy to defeat. If they use it for a timing attack, this is pretty easy to defeat. The final one, and this is the dastardly one. This is really dastardly. We call it a coherent attack. They pop up a transmitter and duplicate the existing satellite signal. And then they make it a little bit stronger, and then they start to drift it away. And for this, there's a few methods. The authentication, the cryptographic authentication is effective. The other method that's effective is what we call trusted reference source, which means to compare its time against a holdover oscillator. If you have a good holdover oscillator, you know how much it can drift. Let's say it can drift 1 microsecond in a day. If it drifts more than that, you know that they're spoofing you. And if you have a very good oscillator, for example, a rubidium, they must drift time by only a tiny bit each day, which isn't very useful. Or they must do it for a long, long time, which increases the chances of detection. So these are the 2 methods that are pretty effective. Okay. Now I want to talk about testing, some real world experience doing the testing. So the first testing that we do, I would call it lab testing. We get a GNSS simulator. It's basically a device that can output all kinds of radio frequencies, and it's got a very nice user interface that lets you design GPS signals. You connect it with a coaxial cable up to your timing receiver. And this is a really good way to verify your algorithms. The disadvantage is you're not going to get surprised here. If you wrote the algorithm and you wrote the test, you're probably going to pass the test, right? What you really need is a room full of people that are trying to hack you. And so for that, we go to open market events. We went to one just a few weeks ago called GetCI, GPS Equipment Testing for Critical Infrastructure. It's put on by the Department of Homeland Security. And then 2 weeks ago, we were at one in Norway called Jammer Test. So Jammer Test is a live sky testing event. It's in northern Norway where there's only fishermen and fish. And there's a mountain range to protect you from Russian jamming, so you can keep your jamming on your side of the mountains. And they do this event every year. They've been doing it for a couple of years now. And it's put on by a collection of Norwegian government authorities. They do it every September. You can see on the right-hand side here, it's at that very northern tip of Norway. It was 38 degrees Fahrenheit there yesterday. So it's a cold place, and you have to wear jackets. And you have peace and quiet to do this. They invite many people from the ecosystem up. There's about 300 participants. I don't know the number for this year. It's grown. Last year was 300 participants. And it's people up and down the food chain for this. They have a pretty extensive list of tests that they conduct. These are jamming and spoofing attempts, and they've got 5 days worth of that. Gotta wait for the photos. Yeah. This is all public information. It's all available on their website. And so, okay, this is what we learned. I'm showing Matthias with a directional antenna here from Norway Jammer Test. The next slides are not about what we learned specifically from Norway, but what we learned from the overall jamming and spoofing mitigation experience. So, basic summary, civilian accidental jamming, it gets a lot of press. It's not really that dangerous. It's easy to protect against, and a holdover oscillator and the RF filters are a pretty good way to solve it. Military jamming is much more serious. So far, military jamming is not on U.S. shores. At first, you think they can't bring it over in a boat. We'd shoot the boat down, but they could somehow get it into the U.S., assemble it, and put it on top of trains, and whatever the spy movie is going to say. We do have to assume this is going to come, and some of these ideas are going to come to our shores. So all the various methods help here. What you really need if you're up against military jamming is terrestrial time transfer, which is expensive. Okay, spoofing. To protect against spoofing, there's a lot of techniques available. The multi-band and multi-constellation receivers are the first thing you should do. The consistency checks are quite effective. Live sky tests have taught us that while there are a number of GPS receiver manufacturers, there's maybe 6 or 8 or so that are well known. There's only a few that really do a good job of it. And it's important to have their receiver in your time server. Authentication is a really strong tool, and the last line of defense is using a consistency check on time. Okay. The last thing is just recommendations for how to build infrastructure. So the basics are, first, choose a good receiver. Make sure it's got RF and IF filters. It should be multi-constellation and multi-band. You should choose a good holdover oscillator. Hopefully the receiver has been field tested in these types of scenarios. And then there's some enhancements you can do. A very easy one is these horizon nulling antennas. They've been deployed in a number of timing applications. and haven't caused any problems. I can't say they solved anything because we haven't had any reports of problems from them. Redundant receivers are effective, especially if you have difficult situations on your roof. And lastly, terrestrial time transfer. That's the one thing that's kind of tough. So that's all I got to say. I took more time than any of my practice zones, but I still made it. Thank you.
So I actually have two questions.
Okay.
The first one is, of the many protections you've mentioned, how many are currently implemented on GPS receivers?
Oh, let's see, on this side. So RF and IF filters are implemented. Multi-constellation, multi-band are implemented. Good holdover oscillators are all there. Horizon nulling antennas, we don't make one, but there are other companies that do. Redundant receivers, we have that as well. So yeah, most of this is available now. Yeah, and there's ongoing work with consistency checks. Yeah.
And the second question is, do you think the solutions in place today focus more on detecting jamming or spoofing and less on preventing it?
Well, we have to assume there's going to be jamming and spoofing, right? I mean, we're not a governmental organization. We can pass law, but it doesn't mean the laws are going to be followed. Yeah, so we're just trying to mitigate it, that if it happens, we have to assume that it will happen. And we have to assume, I mean, for today's problem, I think the equipment works pretty well. But we have to assume that in a few years it's going to get worse in some ways. And we're going to get some surprises. So we have to do the best we can.
Great. Allan, thanks so much. We
Thank you,
really
John.
appreciate it.